Hey everyone, and welcome back to BlackboardAI. Today, we are dissecting a fascinating problem from the recent EPIC Institute of Technology round, Codeforces Round 1036. This problem, part of both Division 1 and Division 2, offers a brilliant insight into how simple observations can solve seemingly complex tasks. If you are looking to sharpen your competitive programming skills, you are in the right place. Do not forget to hit that subscribe button and ring the notification bell to stay updated with our latest problem breakdowns. All right, let us jump right into the problem. We are given an array of length n, where each element I is between 0 and n. Our ultimate goal is to minimize a very specific sum, min of a 1 plus min of a 1 comma a 2 plus dot 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 plus min of a 1 comma a 2 comma dot 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 comma n. To achieve this, we have one powerful operation we can use at most once. Choose two indices I and j such that I is less than j. Then you perform two assignments. A I becomes a I plus a j, and crucially, a j becomes 0. After applying this operation, or choosing not to, we need to output the minimum possible value of that sum of prefix minimums. The problem asks for the minimum sum. This immediately tells us we need a clever strategy. Let us think about how the operation affects the array and the prefix minimums. Our objective is to minimize P1 plus P2 plus dot 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 plus Pn, where Pk equals min of a 1 comma dot 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 comma a k. Remember that prefix minimums are non-increasing. P1 is greater than or equal to P2 is greater than or equal to dot 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 is greater than or equal to Pn. The smallest possible value for any pk is 0. The key to minimizing this sum lies in the operation. A j becomes 0. This is how we introduce zeros into our array, which can then propagate to make later prefix minimums 0, effectively removing their contribution to the sum. Now, here is the surprising simplicity revealed by the solution. The answer is simply min of a 1 comma a 2 plus a 1. Yes, it only depends on the first two elements. Let us rigorously understand why this incredibly simple formula works by examining two main cases. Let us start with the scenario where a 1 is strictly greater than a 2. Initially, our first prefix minimum P1 equals min of a 1 equals a 1. Our second prefix minimum P2 equals min of a 1 comma a 2. Since a 1 is greater than a 2, P2 equals a 2. To minimize the total sum, we want to make as many pk terms as possible equal to 0. The fastest way to introduce a 0 into our prefix minimums is to make a 2 equal to 0. How can we do this using our operation? We choose I equals 1 and j equals 2. We set a 1 becomes a 1 plus a 2, and a 2 becomes 0. Our array now looks like a 1 plus a 2 comma 0, comma, a 3 comma, a 4 comma dot 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 comma a n. Let us recalculate the prefix minimums for this new array. P1 prime new P1 equals min of a 1 plus a 2 equals a 1 plus a 2. P2 prime new P2 equals min of a 1 plus a 2 comma 0 equals 0. P3 prime new P3 equals min of a 1 plus a 2 comma 0 comma a 3 equals 0. And so on. For all k is greater than or equal to 2, pk prime will be 0. So, the total sum becomes a 1 plus a 2 plus 0 plus 0 plus dot 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 plus 0 equals a 1 plus a 2. Does this match our formula min of a 1 comma a 2 plus a 1? Yes, because if a 1 is greater than a 2, then min of a 1 comma a 2 is a 2. So, a 2 plus a 1 is indeed a 1 plus a 2. This operation is extremely effective for this case. Now, consider the case where a 1 is less than or equal to a 2. Initially, P1 equals min of a 1 equals a 1. And P2 equals min of a 1 comma a 2. Since a 1 is less than or equal to a 2, P2 equals a 1. If we were to use the I equals 1 comma j equals 2 operation here, a 1 would become a 1 plus a 2. This would make P1 prime equal to a 1 plus a 2. Since a 1 is less than or equal to a 2, a 1 plus a 2 is greater than or equal to 2 times a 1. This would increase the value of our first prefix minimum unnecessarily, which is not optimal. Instead, since P1 and P2 are already both a 1, which is the smallest they can be without a 1 itself being 0, we want to preserve them and make the subsequent prefix minimums 0 as early as possible. The earliest we can introduce a 0 without disturbing a 1 or a 2 is by setting a 3 to 0. We can do this by picking I equals 2 and j equals 3. We set a 2 becomes a 2 plus a 3, and a 3 becomes 0. Our array now looks like a 1, a 2 plus a 3, 0, a 4, a n. Let us calculate the prefix minimums for this new array. P1 prime new P1 equals min of a 1 equals a 1, unaffected. P2 prime new P2 equals min of a 1, a 2 plus a 3. Since a 1 is less than or equal to a 2 initially, and a 3 is greater than or equal to 0, a 2 plus a 3 will be greater than or equal to a 2, and thus greater than or equal to a 1. So min of a 1, a 2 plus a 3 remains a 1, unaffected. P3 prime new P3 equals min of a 1, a 2 plus a 3, 0 equals 0. And so on, for all k is greater than or equal to 3, pk prime will be 0. The total sum in this case becomes a 1 plus 0 plus 0 plus ... plus 0 equals 2 times a 1. Does this match our formula min of a 1, a 2 plus a 1? Yes again, because if a 1 is less than or equal to a 2, then min of a 1, a 2 is a 1. So, a 1 plus a 1 is indeed 2 times a 1. A quick note on the edge case n equals 2, in this scenario, we only have a 1 and a 2. The operation I equals 2, j equals 3 is not possible. Does our formula still hold? If a 1 is greater than a 2, we perform I equals 1, j equals 2. The array becomes a 1 plus a 2, 0. The sum of prefix minimums is min of a 1 plus a 2 plus min of a 1 plus a 2, 0 equals a 1 plus a 2 plus 0 equals a 1 plus a 2. Our formula min of a 1, a 2 plus a 1 becomes a 2 plus a 1. Matches perfectly. If a 1 is less than or equal to a 2, we cannot use j equals 3. The optimal strategy here is to not perform any operation. The initial array is a 1, a 2. The sum of prefix minimums is min of a 1 plus min of a 1, a 2 equals a 1 plus a 1 equals 2 times a 1. Our formula min of a 1, a 2 plus a 1 becomes a 1 plus a 1. Matches perfectly, so the formula min of a 1, a 2 plus a 1 covers all cases, including the n equals 2 edge case, elegantly. Why is this simple strategy optimal? Essentially, we are trying to force as many prefix minimums to 0 as possible, as early as possible. The first prefix minimum, P1, will always be at least a 1 unless a 1 becomes 0, which is generally not good if a 1 is non-zero. The second prefix minimum, P2, can be made 0 if a 2 becomes 0. If a 1 is greater than a 2, making a 2 equals 0 via I equals 1, j equals 2 is beneficial because a 2 was the second minimum term. The cost is a 1 increasing, but the gain of subsequent zeros outweighs it. If a 1 is less than or equal to a 2, then P2 is already a 1. Making a 2 equals 0 by I equals 1, j equals 2 would just make P1 larger while P2 goes to 0. But P1 would become a 1 plus a 2, which is a 1 plus something non-negative. This is worse than keeping P1 and P2 both at a 1. So, we keep a 1 and a 2 as they are for the first two terms, and achieve zeros for P3 onwards by setting a 3 equals 0 via I equals 2, j equals 3. Any other operation, or not performing an operation at all, would lead to a sum that is greater than or equal to this minimal value. As we have optimally minimized the critical first two terms and made all subsequent terms 0 as early as possible. Now for the implementation, this beautiful observation means we do not need to read the entire array into memory. We only care about a 1 and a 2. Here is a simple C++ implementation. We start by including IOStream for input-output and algorithm for standard min. We read n, then a 1 and a 2. It is good practice to use long for a 1, a 2, and the result to prevent potential overflows, especially since n can be up to 2 times 10 to the power of 5. The most important part after reading a 1 and a 2 is to read and discard the remaining n-2 elements of the array. This clears the input buffer, ensuring that the next test case starts reading from the correct position. Finally, we calculate standard min of a 1, a 2 plus a 1 and print it. This approach gives us an ON solution overall for all test cases combined, as reading the input is the bottleneck, but the computation for each test case is effectively O1. And there you have it, a seemingly complex problem, simplified to an elegant solution by focusing on the core mechanics and critical elements. If you found this explanation helpful, please give this video a thumbs up, share it with your coding community, and definitely subscribe to BlackboardAI for more in-depth competitive programming problem analyses. Do you have a problem you would like us to tackle next? Let us know in the comments below. Happy coding, and I will see you in the next video.